Today we're going to be talking about volumes of revolution. So let's begin with the definition. Solids of revolution, that's an F, are obtained by revolving a region about a line. That is, we rotate a region in the plane about an axis. So some things to note here. In general, the volume of a solid of revolution is given by V equals the integral from A to B of A of x dx, or it's given by V equals the integral from C to D of A of y dy. So if the cross section A of x or A of y is a disk, then we find the radius of the disk in terms of x or y, and we use A is equal to pi times the radius squared. Okay, so if the cross section is a washer, then what we're going to do is we're going to find the inner radius and the outer radius from a sketch. Then what we're going to do is we're going to compute the area of the washer by the following. We're going to compute it by A equals pi times the outer radius, r sub out, for outer radius. And then we're going to subtract pi times the inner radius given by r sub n squared. Not r times n, in squared, r sub in to denote inner. So in other words, what you have here is something like so. So you have your washer where you have from here to here, you have your outer radius, and then from here to here, you have your inner radius. Okay? So that's what's going on. Now, an example. What we're going to do is we're going to find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So what we're doing, we have y equals x cubed, y equals 8. So again, this was y equals x cubed. And then we have y equals 8. And x equals 0. So that's the y-axis. We're going to take this and we're going to revolve this region around the y-axis. So what we really have here, if we're paying attention to what our disk is going to look like whenever we rotate it, then really what we want to do is pay attention to this rectangle created here. So again, that's not really a part of it. I'm doing this to explain a little concept. So if you think about the rectangle from x equals 0 to, from x equals 0 here to y equals x cubed, what we're going to do is we're going to take this and we're going to swing it around the y-axis. And what we're creating here is a disk, right? So picture-wise, what we get when we revolve that region around, we're going to get something like so. And then you have that, if you consider the rectangle moving around, then you have something like that, okay? Where here, this was your delta y, and here, this band is going to be delta y, so it corresponds to that. Then from here to here, you have this is your given by x, and this is your point y, your y value y. So again, this point would be given by x comma y. So that's what we've created. Now, what can we say? Note since we are rotating about the y-axis, it makes sense to slice the solid, that's slice, can make it a little better, perpendicular to the axis and we integrate with respect to y. So again, let's just recall what we did. We took this region bounded by x equals 0, y equals x cubed, and y equals 8. We revolved it around the y-axis. So we sliced this here with a slice that's perpendicular to the axis, and we're going to integrate with respect to y. If we're going to integrate with respect to y, that means we have to solve this for x. So notice that we have y equals x cubed, or solving it for x equals the cubed root of y. Okay? So now we need to find out what a of y is. So a of y is going to be pi times x squared, but that's equal to pi times the cube root of y squared, because that's what we found x to be. And that's equal to pi times y raised to the 2/3. Just rewriting it. Why? Because it makes it easier to integrate. Now, we want to find our volume, right? So to find your volume, we have v is equal to the integral. We're integrating from 0 here to 8 here, because we're integrating with respect to y. So perfect. Integrating from 0 to 8 of a of y dy, but that's equal to the integral from 0 to 8. We replace a of y with what we found it to be here. So doing that, we get pi times y to the 2/3 dy. Pi is constant, so it can come out of the integral. So that's equal to pi times, if you go ahead and integrate, then that's pi times, let's just wait, 0, the integral from 0 to 8 of y to the 2/3 dy. But now you integrate, so you get pi times 3/5 y to the 5/3, right? Because when you integrate, you take your exponent, you have y raised to the 2/3 plus 1 divided by 2/3 plus 1, and that gives us y to the 5/3 divided by 5/3, which simplifies to this. Evaluate it from 0 to 8, plug in your values, you get pi times 3/5 the cube times the cube root of 8 to the 5th. Plug in 0, it's no fun. The cube root of a is 2, or not 8, 8. The cube root of 8 is 2. 2 to the 5th is 32. 32 times 3 is 96. So we get this is equal to 96 pi divided by 5. Now you can take a minute to review this concept. Next, we're going to find the volume of the solid that results from rotating the region enclosed by y equals x and at y equals x squared about the x-axis. So y equals x and y equals x squared. The region here, bounded by that, and we're going to rotate it around the x-axis here. So you have your x-axis, your y-axis. Again, this was y equals x. This was y equals x squared. Not was, it is. Hasn't changed. So what are these points of intersection? You have the origin, and you have the point 1, 1. Okay? Now, whenever you take this region here and you rotate that about the x-axis, then what kind of picture do we create? What kind of solid do we create? Well, let's draw it out. Let's see what we get. So we're taking this region, and what we're going to do is we're going to swing it around the x-axis. So when we do that, then you have this other portion down here, looks just like it. Use your imagination. It's supposed to be identical. You work with my drawing here. Okay, so we did that. So this is what we created. Now, if we zoom in a little bit, zooming in, or thinking about it in terms of zooming in, what do we create here? We have this portion, if we think of our bands, and we have that, right? So what we have here, we have a washer, right? Which is awesome because we get to see another method. So note here, we are slicing perpendicular with respect to the x-axis. And then what we have is, whenever we're zooming in on our washer, a closer look, we have this is our image. It's really shaded. And then you have from here to here, that's your inner radius. What's your inner radius given by? Well, it's given by, if we look back up at our diagram here that we got after rotating about the x-axis, we got this. Well, what happens is this inner circle is formed by the curve y equals x squared. So your inner radius is given by x squared. It's x squared. And then your outer radius we got from y equals x. So your outer radius is given by x. Your inner radius is given by x squared. Why do we care? Because now we want to find the area of our washer in terms of x, because that's what we're slicing with respect to, is perpendicular with respect to the x-axis. So when we find our area, it's in terms of x. That's equal to pi times squared. That's our outer radius is x. We're squaring it. Minus pi times our inner radius, writing x. X squared. That's our inner radius, but we got to square it. So that's equal to pi times the quantity x squared minus x to the 4th. Now we integrate to find the volume. So V is equal to the integral from 0 to 1 of a of x dx, but that's equal to the integral from 0 to 1 pi of x squared minus x to the 4th dx. Pull out your pi, integrate. You have x cubed over 3 minus x to the 5th over 5. Evaluating this from 0 to 1, plug in 1, and plug in 1, you get pi times 1/3 minus 1/5. Plug in 0, you get 0, no 1. So simplify this, you get 2 pi over 15. So that's the volume of the solid that results from rotating the region enclosed by y equals x and y equals x squared about the x-axis. Now for the next example, what we're going to do is we're going to find the volume of the solid obtained by rotating the region in the previous example about the line x equals -1. So again, remember what we had in the previous example. We had y equals x, we had y equals x squared. So again, that was y equals x squared. And then you had y equals x. And then what we're going to do is we're going to take this region here and we're going to rotate the region about the line x equals -1. So if that's x equals -1, we're going to take this region here. We're going to rotate it about this line here. So let's see. We're going to rotate this region about this line. So on this side, you're going to have something like that. And then you're going to have this. Let's make it a little bit better. We can do better than that. So let's make it a little bit better. So at least it looks symmetric, right? So you have y equals x. Then you have y equals x squared. Looks symmetric enough, so you get the idea. Have this region here. And now what we're going to do, since we are rotating around this vertical line, x equals -1, we should think of slicing what we create. The solid that we create, we should think about slicing it with respect to slice it perpendicular with respect to the y-axis, right? Because it's a vertical line. So what do we create? We created a washer, right? So you have this inner one, and then you have, this is your outer radius. So keep this as your idea. This is what's happening. Now, how do we figure out our inner radius from here to here and our outer radius from here to this outer circle? So, again, we need to think about it. We're going to integrate with respect to y. So we need to make sure that we solve these for x. Well, this one's not bad, right? Because we have x equals y. But we have to take into account that we moved over 1. How do we do that? So your inner radius, I'll use green for that. Going up. Remember, your inner radius is from this point to here. So that's given by what? From there to there, we shifted over 1, but from there to there, we had this y. So that's 1 plus y. That's your inner radius. That's a y here. So 1 plus y. Your outer radius, from here to here, I'll use yellow. From this line to here, that's given by, you first have to solve y equals x squared for x. Solving that, you get x is equal to the square root of y, which means that this outer radius has to be 1 plus the square root of y. Okay, Pause the video and review it if you need to understand what we just did, because that is what we need for the setup to find our volume, to find our area. Now, let's write out the note as we have been doing. Note that we are slicing perpendicular to the y-axis. Because we are slicing perpendicular with respect to the y-axis, we need to integrate with respect to y. Perfect. Which means a of y is equal to pi times your outer radius squared, which is 1 plus the square root of y squared, minus pi times your inner radius, 1 plus y, quantity squared. So your volume is equal to the integral. Again, we're going from 0 to 1. That hasn't changed because the points of intersection were 0, 0 and 1, 1 respectively, of a of y dy. And you don't have to take that initial step. You can just jump right to this one if you prefer. So they both will have a pi in common. So let's just go ahead and pull that out. Put that there. So pi times the integral from 0 to 1 of 1 plus the square root of y squared minus 1 plus y, quantity squared, dy. Expand this using the FOIL method. You get pi times the integral from 0 to 1. You might want to take a minute if you need to. I'm just going to give you the simplified version. So again, what you should do is you should expand this using the FOIL method, expand this using the FOIL method, simplify, and what you will get is 2 square root of y minus y squared dy, and that's equal to pi times 4 times y raised to the 3/2, because square root of y is the same thing as y to the 1/2. Remember, you add 1 and then you divide this by 3/2 plus 1. So you'll get 4y to the 3/2 divided by 3 minus y squared divided by 2 minus y cubed divided by 3. Evaluate it from 0 to 1. All we have to do is plug in 1 to see what we get. This is pi times 4/3 minus 1/2 minus 1/3. Simplify, you get pi/2. That's the volume of the solid obtained by taking the region bounded by y equals x and y equals x squared and rotating that around the line x equals -1. Now, to summarize what we've done, we have gone over the disk and the washer methods for finding the volume of a solid. You should review this and know your summary on page 355 of your books. If you have any questions, feel free to ask me. Make sure you go through this information, watch the video again if you need to.